Good morning, everyone. Good afternoon. It is Monday morning, and I realize today I will not be in class tomorrow. I will be on instead junior immersion. Junior immersion. Junior immersion takes me away, but I don't want it to take us away from learning about polar area. So I'm going to choke for a minute. I am going to reuse a video from last year that I made on polar area. It's a little bit long. There's two examples in the video, but one of them is an example that spends some time plotting the points of a polar curve, which is good practice for you if you want to do that. But we did do it in class, so if you want to skip through that a little bit, speed it up a little bit, I think you should pay attention to the area part because it's important. The second example is a better example of a sort of the challenging nature of how we have to look at area under a polar curve different than area under a rectangular curve. So I do suggest you watch that. Otherwise, we'll talk about it again on Thursday, and we'll do a few more examples on Thursday. Enjoy. Okay, area and polar. Let's get down to this. We have found area. It's one of the tenets of calculus. Calculus is derivatives, slope, and integrals, area. We did some derivative stuff last time with finding dy d theta, dx d theta. We did all those things. Now we're going to switch to area. Area is a very popular question on the AP. If there's a polar question asked, area will be involved. Now, in rectangular coordinates, we mainly dealt with rectangles in rectangular coordinates. That's because we have very nice setup for that. We have like an x value, a dx value, and then a y value. And if we multiply those things together, we get the area under this rectangle. If we add up all of those areas, we get an approximation for the area under the curve. There we go. We made these things widths of 0, so that we got the exact area under this curve precisely. That was very useful for us because we have an x and a y coordinate plane, and that gives us good rectangles. In polar coordinates, we don't have that same ability. So instead of looking at things in terms of x and y, we look at things coming out from the origin. So I drew some examples here of these triangular shapes. We don't really care about the triangle too much, but what I want to focus in on is that we start from the origin and we go out to the line. All of these areas added up would give us the full area under the curve. We don't go up and down like in rectangular coordinates because that would be complicated over here in this part because you have like a up and a down. But also this is just not how our system works. Our system works as the R starts, we start at an angle and we go out R length. And so all of these things combined give us the nice area under this curve. So I'm going to do this quite a bit, and I need you to try and think about when we're talking about area and polar stuff, we're talking about from here out, from here out. Drawing these a little partition helps us think about, okay, what area am I looking at here? Great. So we get this this area equation in polar form. I'm going to leave these lines on because it might help. Maybe it won't. I don't know. We'll see. The area equation in polar has a few things. I'm going to ignore kind of this one because most times we're given the equation in terms of r. R equals like 3 cosine 3 theta. But we have a 1/2 integral from alpha to beta. These two things are angles. I'll show you in a second. And then this is r squared. It's our equation squared. The two things that we will forget the most often are going to be our 1/2 out front. We will always forget that. And then our squared is a hard thing to remember. So we just have to remember 1/2 r squared. So this alpha and beta, if I were to look at this thing again, I would like, what's the area from this angle here to this angle here? That would give me the area of this like slice in between. So alpha to beta ignores all of this under area. It just goes from alpha to beta of like a interesting little pizza slice. Should we try an example? Yes, we should. 5-6 minutes into this video, let's try one. Here is an equation, 3 cosine 3 theta. It is a rose, there is a petal, this is a flower. Hopefully we can graph this. I am going to graph it, let's see, I'm gonna make just a simple X and Y, and we'll talk about this in a second, but I'll make a simple X and Y, or R and theta R chart. But before we do anything, I'll do this by hand. We could plug this into a calculator for sure, and I'll show you at the end when we check the answer with our calculator. I'll show you, but I think for the most part, I would love for you to be able to at least have some recognition of how this graph moves, because that helps us a lot to figure out what angles we need for our bounds. So let's just take a look at this little equation really quick here. If we have r equals 3 cosine 3 theta, the angles that I really liked with cosine, I really liked the cosine of 0 because that was 1. I really liked the cosine of pi over 3, I guess, because that was 1/2. And I especially liked the cosine of pi over 2 because that was 0. I like those 3 angles. I'm going to stick there. But we have a 3 theta involved. So I'm trying to think to myself, how can I get these angles going on? But if I plug in pi over 3 into this thing, I'll get 3 times pi over 3, which is pi. And that just skips ahead way too far. So I think the angles that I can try to attack here is an angle like pi over 9. Because 3 times pi over 9 gives me my pi over 3. And also an angle like possibly pi over 6. Because pi over 6 times 3 is my pi over 2. And I think any combination of those things, like maybe a 2 pi over 9, that would give me a 2 pi over 3 when I multiply it. Those are the angles that I'm going to try to attack here when I graph this thing, because they'll give me nice values. So let's just start with maybe theta equals 0. And I would get, this would be 3 times the cosine of 3 times 0, which is not 0, it's 3, I think. The cosine of 0 is 1. 3 times 1 is 3. So I will plot that right here on the graph. Theta equals 0, r equals 3. That means I go with my angle 0 and my r value is 3. Fantastic. Let's keep going. Like I mentioned on the right, pi over 9 is another good angle because I'll get 3 cosine of 3 times pi over 9. 3 times pi over 9 is pi over 3. Pi over 3 cosine is 1/2, so I get 3 halves. 3 halves. Now here's the issue. I don't know exactly where pi over 9 is. Maybe, let's see, okay, this is pi over 4. So this is like pi over 8. So pi over 9 is probably right here-ish. I don't think it matters too much. And in fact, it won't matter too much. We're just trying to get, again, a simple best estimate of this graph. Let's keep going so I don't start rambling. What's our next angle? Would be pi over 6 is what we said. That's 3 cosine of 3 times pi over 6, which is pi over 2, which is 0. So that's 0. Oh, great. 0 right here. So if we start to graph this, it starts here and it kind of goes in this direction. Now we'll see what happens, because in our example in class last week, we saw this thing kind of go over here and then make this apple shape. I don't think that's going to happen here because it says it's a petal and a rose. I think things are going to go a little bit different for us. What's a good angle now to use? Oh, well, the next one I think would be 2 pi over 9. And this is, again, unfortunately, I'm going to keep using the word mathematical intuition. If I want the 3s, I looked over here and I think, okay, my pi over 9s are going to be good. The next one I could do is like 3 pi over 9, which is pi over 3. That one's going to be a good one. Or this one right here, 2 pi over 6, which is going to be also pi over 3. But we just got to start plugging some things in to get to incrementally step through our function here. Let's see, this would be 3 cosine of 3 times 2 pi over 9, which is now 2 pi over 3. The cosine of 2 pi over 3 is up here. That would be negative 1/2, I think. So this would be negative 3 halves. Oh gosh. Okay, how should I do this? This was 0. This is pi over 9. This is pi over 6. Maybe this is 2 pi over 9. That's pi over 4.5, so maybe a little bit less. I'm going to have to guess this one right here. But again, with a negative r value, if we remember this, we're going to go out to our angle. Say that's our angle there at 2 pi over 9. And then we're going to go backwards, 1.5 backwards. So I'm going to maybe make it a mark right, oh gosh, here. I really don't know. But again, it's the best guess. Here I thought was pi over 9, so this is 2 of them. I went backwards, 1.5. There we go. Fantastic. Let's keep going. Pi over 3 is my next angle. I'll get 3 cosine of 3 times pi over 3, which is pi, which is negative 3. You can pause the video and think about that for a second if you need to. But that would be my angles pi over 3. Maybe that's the angle like right here. Pi over 3 right there. So I go backwards 1, 2, 3. 1, 2, 3, like maybe like right there. And then what's my next angle? Must just be pi over 2, I think. I'm just going through like some unit circle things. Pi over 3 and then pi over 2. Yeah, sure. 3 cosine of 3 times pi over 2 is equal to, oh, it's really hard to see. Those are the angles. Whatever. 3 cosine 3, okay, so 3 pi, 0. That is 0. Cosine of 3 pi over 2 is 0, so 3 times 0 is 0, which means I'm back here at 0 again. Maybe I can make that little green spot there. So here's my graph. It goes here, it curls around, it comes down here, and then it curls back to the origin. We can kind of see a pattern evolving here with like a 3 halves 0, negative 3 halves 3 0. So I'm thinking I'm going to stop doing this because it's just going to take too much time. So I've gone here, 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 here. I'm going to wrap back up around here. I think I'm going to go to the 1.5, out to the 3, and then back to the 0. Like the 1.5, out to the 3, back to the 0, and then to the 1.5, back to the 3. There we go. There's our nice little graph. We've gone around the horn all the way like this in one swoop. Great. Fantastic. Now let's talk about some area, because I want to find the area of one petal here. One petal. And that's maybe a little bit complicated, but we can start to think about this in a couple of different ways. Let's just say I start at 0. If I start at 0 here is 0. And I start to accumulate some area by going through these angles here. So I'm at 0, and then I'm adding some area, adding some area, adding some area. This angle right here was my pi over 9. That was that angle right there, and I'm going to keep going here to here to here to here to here to here to here. Now, what angle was this when I got back to 0? Well, that was pi over 6. So I've gone to do this one little half petal from theta equals 0 to pi over 6, and I could use that to my advantage. Symmetry happens a lot in these polar curves. We saw it here with the R values, but it happens all the time. So I can use the fact that this is the top half of my petal and this is the bottom half, but I could just take this thing and double it. Let's do it. I could take this thing and say that my area is going to equal, let's double it. We'll go 2 times 1/2 the integral from 0 to pi over 6 of 3 cosine 3 theta squared d theta. This inside part here is just the integral, the area from here to here, from 0 to pi over 6. The 1/2 is included in my area equation. So is the squared. I didn't forget either of those things. Applaud me now. Pause, applaud, great. Oh my gosh, we're at 1540. This is not going to be any better than the first time. I doubled it to get my area under the curve. Okay, fine. Let's think about a different way of doing this. I could also say, all right, I've gone from 0 to pi over 6. I've gone from 0 to pi over 6. Now I'm sitting right here in the middle. That's just half a petal. Could I come up with a whole petal? Absolutely. I could go from pi over 6 and go around this whole way back to 0. And I think that would be like from pi over 6 back over to pi over 2. From this 0 to this 0, that wraps me around 1 full petal. See how I kind of started at the 3? That's starting in the middle of a petal. But if I go from 0 to 0, that's going to give me 1 whole petal. In that case, I would get the integral, I would get 1/2 the integral from pi over 6 to pi over 2 of the same inside bit. I'll just duplicate that to speed up some time. And we should get the same answer for both of these things. Let's take a look at our calculator and do it. A couple things. Our calculator does have a polar mode. If we go to apps, you can see that there's a parametric. We tried that once. But we also now have a polar mode. Polar allows us to type in like 3 cosine 3 theta. If you hit your little theta button up there, I can't show you because it won't show you, but the little xt theta n button, it'll give you a theta. And if we plot it, oh, I can't zoom in. Okay, fine. It gives us a little 3 petaled rows, which we got. Nice. Fantastic. But I don't want to be in polar mode. I don't want to be there because, I mean, you can do integrals if you're here. You can do integrals in polar mode. But I think that sometimes there's been some issues with that. And I think you should just go back to function where we're comfortable, and we can do it. So we'll do this first one. 2 times 1/2 times the integral from 0 to pi over 6 of 3 cosine 3 x, 3 theta, whatever, dx. That was my half petal times 2, and I'll get an answer. Or I did my other one, which was just 1/2 times the integral from pi over 6 to, oh gosh, pi over 2 of 3 cosine 3x, where did I need to square it? Right there, squared dx. And yesterday when I did this video, I got 2 wildly different answers, but today I'll get the same answer. 2.35619, 2.356. So the area here is 2.356. Perfect. 18, okay, so I saved us 2 or 3 minutes by doing that without any mistakes. So maybe my first video wasn't so bad. Let's try another one. I'm now feeling better about myself. This is one where we graphed it ourselves and found the area using 2 different methods, symmetry. Let's look at this question. Slightly a little more complicated, but thankfully we have the graph for us. This is a cool, I don't know what it's called, a limnicon? I don't know. I can't remember what the name of it is. But it's this graph that kind of loops around itself. Let's take a look and just explore this for a few seconds here. If I have my r value, let's just say my theta equals 0, what happens? That means that r equals 1 minus 2 sine of 0, which is just 1. If you have a graph like this, you're given the graph, you should always, oh, it's very hard to see. I have lines in there, but they're just not going to show up. Very interesting. Okay, so I'll be able to see them, but you won't be able to. Hopefully on the notes, I can make them darker. When you have a graph, you should always plug in 0 to figure out what is my starting point. My starting point here is at 0, 1. And then I just have to decide, am I going this direction or am I going this direction? I don't know. Let's figure it out. Let's plug in another little value like theta equals pi over, I don't know, what's a good angle for sine? 6? That's r equals 1 minus 2 sine of pi over 6, which is going to be 0. Oh, cool. That must be this angle right here-ish. That's that angle, that pi over 6 angle, which means my value is right here. So let's jot those down so we can keep track of them. This is theta equals 0. This here, the first time it happens, is theta equals pi over, over 6. That's the first time it happens. Great. Great. So now we know that it goes kind of in this direction. Let's talk about what the area means in this thing, because we have to think about what our angles are going to be. It says I want to find the area between the inner and the outer loops. What does that mean? Here is the inner loop. Here is the outer loop. I want to find the area in between those two things. And if you're thinking to yourself, okay, I can just do some simple subtraction and do like the top minus the bottom thing, yes, we will kind of get into that realm of things. But think about this. When I do area of a polar curve, I start at, let's just see if we can do this. I start at the origin and I go out, yeah? I go out. I accumulate area in this way. Let's see if this is gonna work for me. I'm going along, it's gonna zoom in. Okay, fine, just ignore the zoom in. I'm going along my curve and I'm accumulating area, right? I'm adding up all of the lengths of the pink lines. I'm capturing, so from 0 to pi over 6, I capture this first little top hump of my shape, which is area that I do want. I absolutely want that area to be a part of my whole thing. But then what happens is as I go around, so think about this. Your area you should think about as if you are a person walking along this green line, holding a rope at a certain point, like a rope is staked here at the origin, and you're walking along and you're measuring the distance of the rope every time and you're adding all that up to get the area of this little, I don't know, patch of grass or something. You're walking along, right? And then you walk this way along the green line. Oh, my zoom's gonna get in my way. You're gonna walk along this way. So you start here, you're walking, you're walking, you're walking, you're still walking, you're still walking. I'm capturing all the area of this inner loop. I'm still walking along the line. I'm gonna keep walking out. I'm gonna keep walking, all the way around back to where I started. Was there an issue with that? Absolutely there was an issue with that. The issue is this. As I walk the first time, I'm capturing all this inner loop area, right? As I walk along this inner loop, I'm capturing all of that area. And then as I go around the outside, what happens again? I capture this area a second time. I don't want that area to be captured a second time. I want it to be captured one time. So as I go through here, I'm gonna have to say, I want all this area, but then I wanna delete some of the area. So if I look at this, if I start to maybe just shade it a little bit, I'm gonna shade, like as I walk around, I'm gonna capture this area, this area, this area, this area. Well, let's see if I can do this. The first time I walk around, I'm gonna start capturing this area, and I go around here and I start capturing, and I capture all of this area here, right? But then I keep walking around. Let's make it a little bit bigger so I can not have to do so much. I keep walking around, right? And as I walk around, I capture all of this area again. But what happens when I capture the area again is I capture this middle inner loop part again, twice. And I don't want it. I don't want it at all. So what do I have to do? I have to delete it. Oh, that's not gonna work. I was gonna try to do the whole thing. I have to delete it twice. I wanna get this area out of the way. It's there twice. So I'm gonna have to delete it twice. So I think what our plan should be to go from here all the way around the horn. I keep saying that, I'm not sure why, because I'm 25 minutes into this video. I'm gonna go all the way around back to our starting point, and I'm gonna take out this part twice. Let's get a few more angles to figure out what we're going here. Let's try theta equals pi over 2. That means that r equals 1 minus 2 sine of pi over 2, which is 1, which is negative 1, right? The sine of pi over 2 is 1. 2 times 1 is 1. 2 times 1 is 2. 1 minus 2 is negative 1. So if I were to look at some colors here, this point right here is right here. So this is pi over 2. Do I get back to 0 somehow? Let's see. I must, if theta equals maybe 5 pi over 6, that means that r equals 1 minus 2 sine of 5 pi over 6. Sine of 5 pi over 6 is positive 1/2, so then I get 1 minus 2 times 1/2, so I'm back to 0. So this angle again right here is on the underside is 5 pi over 6, which is great. And then let's just make sure that my pi should be negative 1. So I'm now at pi, which means that r equals, 1. 2 minus sine of pi. What's the sine of pi? The sine of pi is 0, so I get 1 minus 0 is 1, and that is, incidentally enough, this point right over here. Because my angle is pi, and I'm going out positive 1, That's my angle. So this is all working out great for us. I was just trying to figure out how far do I have to go around to get back to my starting point. Is it going to be like in this one where I go from like 0 and I swoop around, and by the time I hit pi, I'm back to the starting point? This is like has like a period of pi. This one though has a period of 2 pi. It seems I go 0, pi over 6, pi over 2, 5 pi over 6, pi, and then I must sweep around 4 pi over 3, 3 pi over 2. Let's just make sure that that 3 pi over 2 hits. 3 pi over 2. That's r equals 1 minus 2 sine of 3 pi over 2. The sine of 3 pi over 2 is -1, so I get 1 minus 2 times -1, which is 1 plus 2, which is 3. That is this point right here because I'm going in the 3 pi over 2 direction, 3 units down. Fantastic. So then, okay, so 0 to 2 pi works for me. Great. I'm back to 2 pi at the end. So let's figure out some area here. Let's take this work here and make it small over here. And let's come up with a nice area equation. Area is equal to. Let's find the whole thing. Now there's lots of ways of doing this. We could piecemeal this up and go like from, we could piecemeal this up and go from like here to here and then skip out this area and then go from here to here. We'll try that in a second if we have time. 2742, crap. 1/2, I'll calm down. I realized I was talking pretty fast here. 0 to 2 pi of 1 minus 2 sine theta squared d theta. That gives me my area of the whole thing. But what I want to do is subtract out minus 2 areas, 1/2 pi over 6 to 5 pi over 6 of 1 minus 2 sine theta squared d theta. What that will do is that takes this pi over 6 to 5 pi over 6 and it subtracts it 2 times. This is once, which happens the first time I pass through. It captures all the area. And then the second time I pass through, it captures it again, and I don't want any of it, so I'm going to minus it twice. And that should give me my total area equals. Or I could do this. Maybe I'll write this out a little bit less formally. But I'll do 1/2 from 0 to pi over 6. That captures this piece right here, this 0 to pi over 6. I'm going to skip out on the pi over 6 to 5 pi over 6 completely because I don't want it at all. So then I would do like whatever r squared d theta. And I'm going to add to it 1/2 the integral from 5 pi over 6 to 2 pi of r squared d theta. That thing goes, so I skip out on this whole part here, but then I go from 5 pi, oh shoot, this is still going to be an issue though, because 5 pi over 6 over here, it gets this again, right? The 5 pi over 6 all the way to the 2 pi captures this inside part. So then what I have to do is I have to say, okay, minus one of these 1/2s from pi over 6 to 5 pi over. So I can't really avoid it, right? I tried to avoid it here by just going between, like skipping the 5 pi over 6 part, but then I forgot that it captures it again. This would give us the same answer as this. Let's just verify. Let's see if I can remember how to do all this. Let's go. We'll go 0.5 times the integral from 0 to 2 pi, that's 23, 2 pi of 1 minus 2 sine theta squared d theta. Now I'm going to give that as one integral. Sometimes when you subtract integrals and start to combine them, it gives you an error on the prime. So then I was going to go, oh, can I just be smart here and just say that this 2 and this 1, so I'm doing this one right now. This 2 and this 1/2 is just going to cancel out. I don't really need to do a 2 times 1/2. So I'll just take the integral from pi over 6 to 5 pi over 6 of 1 minus 2 sine theta squared d theta. Any mistakes so far? You're probably screaming at me. And I'll just do this thing minus this thing, and I'll get my answer of 8.337. 8.337. That is the correct answer, 8.337. If we did it this way, I think we get the same thing. I don't really want to spend the time typing it out. If we don't, for whatever reason, we could talk about that, or you can talk about that. The last example, last two are when we look at two different graphs. We talked about this a little bit in class last week with the Earth, the satellites, and intersecting at different points. We'll do this when I get back on Thursday. I think that there's more discussion to be had. I think doing these things and figuring out what these areas are is a good starting point for you to look at. I will assign some questions that just have to do with single curves, and we'll do that first. And then the double curves we can talk about together. It's a crapshoot in terms of what the AP is going to ask. We've definitely seen questions like this, and we've seen a lot of questions like this too. So we will have to look at both of them. But for now, area under the curve, as just a little recap, is a nice little angle to angle. We think about things this direction, right? Coming out, coming out, coming out. That was best on display here. So great.